Okay, welcome back. So now we're going to learn how to actually calculate the rotational inertia of an extended object. And so the table that's in the textbook that has all the different values, such as the 2/5 mr squared for a sphere, this is where that comes from. So this is the essential question for this lesson. How do we do it? How do we calculate the moment of inertia of an extended object? And the strategy is going to be pretty simple. There's a couple things that we can do. First, for a system of particles, we have I is the sum of mr squared. But for a solid object, we have I as the integral of dm r squared. So what we're doing is we're taking the mass and we're splitting it up into lots of itty bitty pieces, dm, which each have a distance of r from the axis of rotation. Once we do that, then we can move it around using the parallel axis theorem, which says that I is equal to I of the center of mass plus the mass times h squared. So we'll talk more about what this means a bit later on. We're going to dive right into a practice problem here. We're going to derive the rotational inertia of a long thin rod of length L and mass m about a point 1/3 of the way from one end. Okay? So the first thing that we want to do is draw a picture. So here's the rod. Okay? And 1/3 would be about here-ish. Okay? And so that means that basically if I go this way, I'm going to have 2/3 of the rod. And if I go this way, I'm going to have 1/3 of the rod. Okay, so what I want to do is I want to consider a small piece of the rod that is going to have a mass of dm and a length of dx. And what's going to link this together is that this is going to have a linear density of the total mass of the rod divided by the total length, which is equivalent to the mass of a small piece over the length of a small piece. So this is going to be extremely useful when we're setting this up. Okay? So our equation for part A is that we want to integrate r squared dm. Okay, now r in this case is how far we are from the axis of rotation. And if we set this up so that the axis of rotation is at x equals 0, well, then what we're really integrating is the x coordinate of this chunk of the rod. And what we're going to have to do is integrate that from negative L over 3 to 2L over 3. So r squared is going to turn into x squared, and then what we're going to have to do is find a way to replace dm. But if you look up here, kind of like, whoops, put that back. Kind of like when we did our momentum calculations, we can say that lambda is dm dx, so our center of mass calculations rather. So dm is equal to lambda dx. Lambda is kind of a placeholder. We will replace it when we're all done. But this allows us to then write, oh, here we go, that I is equal to the integral from negative L over 3 to 2L over 3. Let's clean that up. Of x squared times, stop it, lambda dx. Okay? Now that's something that we can evaluate. So it'll be lambda times x cubed over 3 evaluated from negative L over 3 to 2L over 3. So there'll be lambda times, let's see, 2L over 3 cubed. Okay, let's take that that 3 out in front. So it's just going to be lambda over 3 x cubed. So then we're just going to have 8 L cubed over 27 minus, and I'm sorry, that's not clear, but that's just L over 3, minus negative L cubed over 27. Okay, so that's going to give us lambda over 3 times 9 L cubed over 27. Okay, and simplifying this a little bit more, we have, first of all, that lambda is equal to m over L. So I'll write that, m over L is lambda. And then that's going to be a 1, that'll be a 3, that'll be a 1, that'll be a 9. So this is going to give us L cubed over 9, or just simply, sorry about that, 1/9 ml squared. So that's part A, doing it by integration. And you can see that we have an answer that is in terms of mr squared with L replacing r, and we have 1/9 out in front. Now in part B, what we're going to do is we're going to use the parallel axis theorem and the rotational inertia of a rod about the center of mass, because I about any point is equal to I center of mass plus mh squared. So remember, h is how far you're moving it, and we can do it that way. Let's switch to a different color so we can see that we're doing something different here. Okay, so now let's think about this. The center of mass is at L over 2, so if this is 0, okay? And if we're moving from there to L over 3, well, how much is this distance h? It's really L over 2 minus L over 3, which is L over 6, right? Right, okay. So now let's go ahead and plug that into here. It turns out that I, for the center of mass of a rod, is 1/12 ml squared. And that's something that you can just look it up. You're going to have to trust me on this. Okay? Then we have m is m, and h is L over 6. So squared is L squared over 36. Okay, let's evaluate this. That's 3 over 36. And so that gives us 4 over 36 ml squared. And I don't need to reduce this because you can see immediately that that's the same as 1/9 ml squared. So that's a good check, and it tells us that we've done our integral correctly. Okay, now we can finally scoot ahead to this next practice problem, and we want to derive the rotational inertia of a ring of mass m and radius r about its center using I equals integral of r squared dm. Okay, so here is a ring that, pretend like it's ringy. Okay, so it's a ring, pretty thin, so it has a mass of m and a radius of r. Okay, and we want to essentially use the definition here that I is equal to the integral of r squared dm. So we need to identify what a small piece of this ring would be. So here it is, and this small piece would have a mass of dm, and it would have a length of ds. So whenever you're going in a circle, s is better to use than x, y, or z. Okay? And so s is equal to theta times r, so ds is equal to r d theta. Maybe I'll write it that s is r theta. Okay? And also, we know that the density of this is m over 2 pi r, which is the same thing as dm over ds. So ds whoops, sorry. So dm, which we're going to need, is lambda ds, which is lambda r d theta. Okay, so now I is the integral, and we can just go from 0 to 2 pi of r squared dm. But dm is lambda r d theta. So far, so good? Okay. So now we see what else we can do with this. And we can do a couple things. First of all, well, before I integrate, I'll do one more step. So basically, little r right here is not changing. It's just going to be big R. So it's going to be lambda r cubed d theta, which is really cool because none of that is actually changing with respect to theta as we go around. So it's just going to be lambda r cubed times the integral of d theta, which is just theta from 0 to 2 pi, which is just 2 pi lambda r cubed. The last thing that we need to do is get that lambda out of there and recall that it's m over 2 pi r. So it's going to be 2 pi r cubed divided by, whoops, times m over 2 pi r. And we get the not so surprising result that I is equal to mr squared. Why should that not be surprising? Well, because if this ring was made of a chunk or bits and pieces of little particles, we would have to take the mass of each piece and multiply by the distance of each piece to the center squared. And each piece of mass little m is the same distance, namely r. Okay, so it's really basically when we do the integral of r squared dm, we're really talking about the integral of dm times r squared, and the integral of dm is just m. So we really didn't have to go through all of that, but I just wanted to show you another example of how this would be set up. Okay, so next time we're going to start getting into rotational dynamics, and so we'll be talking about what does force look like when we have rotation.